Hi everyone. We have another snow day tomorrow. So I'm making a second video today for you to enjoy tonight or tomorrow, tomorrow being Tuesday, and hopefully I see you on Wednesday. Like I said in the last video, because of the snow days and I haven't seen you for February vacation as well, volumes are kind of just on your own. You're learning this, and I'm really hoping that you watched. I know the video was long. It was long for me to make too. The first video was a little long, but it was an intro. It was going to be the whole long block. This is what we were going to do Tuesday, where we're going to be practicing volumes of revolution. I have some problems I'm going to have you do. I'll do some with you, and then we were going to practice some free responses, and I have some visuals for that. So that's what this video is going to be. We're going to start with two half sheets, and there's really we're not going to be doing like calculations though, actually doing any antiderivatives. These half sheets are all about the setup, because the setup is extremely important, and like imagining the radii, big R, little r, is it a disc, is it a washer, stuff like that. So that's what these are going to be. Then we'll start some free responses where sometimes you actually have to do the problem out. These are going to be posted as PDFs, and if you have a printer, highly recommend, I'm going to ask that you print these. If you can, I know you might not have a printer, or if you do, it might not have ink. So if you don't have a printer, then you're just going to write your answers in your notebook. As you can see, it's literally a box. So like all you're going to be doing is drawing axes and labeling R and V. So if you can't print this, it's really not a big deal. You can just label your work A, B, C, D, E, F for the first one, and the second one A, B, C, D, E, F. And again, it's just the setup. So don't think you're going to be spending like an hour doing antiderivatives and evaluating anything, okay? So in the last video, we practiced setting everything up and imagining the visuals, talking about discs and washers. And just as a reminder here, I'm going to write this down here. Our formula, if it was, oh darn it, I keep doing this, getting it too close here. Sorry, one sec. Come on. Okay, that is B. Was pi big R squared minus pi little r squared. And I'm going to put something here that I didn't say before. It's dx or dy. So this video is going to be exciting because we're not just going to be rotating around a horizontal axis. We're also going to be rotating around a vertical axis, which we haven't done yet. We'll use calculus and motion to help picture it because, again, the visualization is huge. Now, the cool thing about these problems is it's the same exact area every single time. You're just rotating it different ways. I'm going to do probably 3 of them with you, and then I'll leave the other 3 for you to do on this sheet. Once you get the hang of it, it goes pretty quick. So I need to find the region bounded by this line. Y equals 0, that horizontal line, x equals 2, that vertical line. Okay, so let's go ahead and draw this. All right, so I have 1/2 x plus 1. And you might notice there's these little bubble statements right here. Whenever you do this, I'm going to go through each step with you. So the first thing I'm going to do is plan my spacing. So I don't really have to plan much here because the axes were drawn, but notice all these other ones, like there's no axis drawn. So sometimes you're going to want your y-axis like your x-axis way up there. Sometimes you might want your x-axis all the way, oh my God, your y-axis all the way there. It's just depending on like where you're going to rotate. So the planning can be important. Otherwise, you're just going to run out of space. All right, so that's the first thing we're going to do. Plan our spacing, which again, for this one, I really didn't have to do too much. So I'm doing 1/2 x plus 1. I got this line, whoop, and it would keep going. I have the line y equals 0. That is this horizontal line, and x equals 2. That is this vertical line. So the area bounded by all of this is going to be this area right here. And that's what I'm going to rotate. So we're going to rotate it around the x-axis. So I'm going to draw this here to show I'm bringing it around here. There's my x-axis. I'm going to draw my little reflected region down here. So there's the reflected piece. And now I want to imagine if I were to chop this up, how would I chop it up in order to get circles? Just so you know, the second step here was to draw the region, which we did, and then draw the reflected region, which we did. Highly recommend you jot these down for yourself. Okay, step 4. Why don't I have a step 4? I don't know. All right, that must have been some kind of typo. Anyway, we'll make that 4th and that 5th. So we're going to decide how we're going to cut this up in order to get circles. And then you have to decide, okay, is it going to be a disc or a washer? And in a moment, well, in a few minutes, we're going to chop horizontally here to get discs and washers. So far, at least with me, you've only done this cutting it up vertically. Okay, clearly if I chop this way, I'm going to be getting circles. So I'm going to be choosing, oh my God, there we go. This one. Okay, last step is to draw little r and big R, and then we're just going to go ahead and fill in the statements at the bottom. Remember, you connect little r and big R to the original area, not the reflected area. So before I do anything else, I want to get this going on Calculus in Motion so you can see it. So I'm going to pause it quick. All right, I got it. So here's what's going to look like. Here is my 1/2 x plus 1. Here's my horizontal line, and I'm going to go ahead and hit revolve. Woo, there we go. All right, I'm going to sweep one disc / washer, and you should be able to see pretty clearly this is definitely a disc, like a tortilla. Okay, there's nothing hollow about this. And you should also notice that my circle, as I'm chopping it to the right, the radius is getting larger. So my radius, I'm going to need an expression for it. Another thing you need to notice is where do your circles, really they're cylinders, remember, you add volumes to get total volume. Your cylinders are starting at this x value of -2, and you chop all the way over here to 2. All right, so on my diagram here, my cylinders start at -2. I'm just going to draw a random cylinder here, and that way I can draw the radius. You should always be drawing the radius. You can draw more than one cylinder if you want to help yourself visualize it, so you can see the radius actually getting larger, but you definitely don't have to do that. I'm going to cross this off because I don't have a big R and a little r. You can put your answer here or here. It really doesn't matter because you only have one of them going on. And we're going to do distance between 2 points, a vertical distance between 2 points. I'm going to subtract the y values. So the y value here is the function itself because that's changing. 1/2 x plus 1 minus the y value down here is 0. So I have 1/2 x plus 1. Okay. And then my volume is going to be the integral from, okay, my cylinders start at -2 and my cylinders end at 2. And I'm going to do pi r squared times height. And your height, remember, was this little infinitesimally thin width, okay, because your radius is the thing going up and down. So 1/2 x plus 1, pi r squared. And that's it. So I'm going to get the next visual ready for you, and then we'll keep going. All right, you ready? Let's go ahead and do C together, and then I'll mix it up and do one where we are revolving around a line with X. Okay, so for this one, we want to revolve around y equals 4. So let's think about this for a minute. I need to plan my spacing. So I'm revolving around y equals 4. My drawing ended at y equals 2. So I need to go all the way up to 4, and then I'm going to rotate around 4, which means I'm going to be way above 4. So when I plan my spacing, I'm going to make it so that I can go all the way up to, I think I want it to go up to 8. Let's see here. All right. I'm going to put my x-axis way at the bottom here, and let's just quickly draw. Remember, the area stays the same every time. I have 1/2 x plus 1, right? So it looked like that, and I'm going up until x equals 2 and y equals 0. There was our two-dimensional area, and we are going to rotate this around y equals 4. So go ahead and draw yourself a horizontal line at y equals 4, and 1, 2, 3, 4. So there's my line of reflection. I'm going to rotate around that. And let me make this darker so you can actually see it. All right, so now I have to figure out, okay, from this furthest away line to the line of reflection, 1, 2, 3, 4, 1, 2, 3, 4. Let me go ahead and draw the reflected piece. I'll put that in purple. So there is what it's going to look like. And then 1, 2 away, so 1, 2 away. This doesn't have to be perfect, but just, you know, to make sure you're visualizing this properly, this is what's going on here. Whoop. Okay, so let's go ahead and Calculus in Motion and see what this is going to look like when I rotate the red area around the line y equals 4. So here's my line of rotation, the axis of revolution. Are you ready? Here we go. We're going to bring it all the way around. So this is a very large hollow in the middle there. I'm going to go ahead and sweep a disc or a washer. This is definitely a washer. There's a huge hollow there in the middle, and the hollow does get smaller as you move to the right. And I want you to notice, is either radius staying constant? You should be able to see an inside circle and an outside circle. So let me pause it here quick. Your inside circle is right here, and your outside circle goes all the way from the top to the bottom. So your inside circle is getting smaller and smaller as you go. The outside circle is actually staying constant. So big R is going to be constant here. So I'm going to revolve this one more time just so you can make sure you're totally good on what's happening here as this rotates around. All right, let's try to replicate that as best as we can here so we can mark it up. I'm going to put mine here. It doesn't really matter where you draw it as long as you can draw a little r and big R. That is a really wobbly circle. So here's my dx, the infinitesimally small width, and I'm going to draw little r and big R. Now remember, you draw little r and big R to the original area, okay? So whenever I draw this, I always say this to myself. I'm going to start from the line of revolution, and I'm going to draw until I hit the inside function. Whoop, right there. That's little r. And then I'm going to start over from the line of revolution, always. Keep drawing until you hit the outside thing, which is right there. There is big R. A little hard to see. Sorry about that. I need to write expressions for little r and big R. So I'm going to put those down here. Now, we said big R is going to stay constant. So the distance between two vertical points, let me subtract the y values. So the y value here is 4 minus the y value down here is 0. 4 minus 0 is 4. Now let's go ahead and do it for little r. I'm going to subtract the upper y value, which is here. That's always going to be 4. Minus, okay, what is the lower y value? The lower y value is here. And depending on where you draw little r is going to be a different length. But no matter where you draw it, the bottom part is always on this function, which is 1/2 x plus 1. So 4 minus quantity 1/2 x plus 1, which you can of course simplify. That'd be negative 1/2 x. That'd be minus 1. So 4 minus 1 is 3. All right, so let's do a volume. My cylinders start at -2. They go up until 2 still. And I'm going to do pi big R squared minus pi little r squared. Negative 1/2 x plus 3 squared, all dx. And I'm going to put parentheses there. All right, cool. Now let's go ahead and mix it up. I'm going to do part D with you all. You can fill in the other ones. So I want to rotate around x equals -2. So let's go back to our original area. And this time I'm going to rotate around x equals -2. So I'm going to be spinning around this way. So that means I'm going to take this region and put it over here. So I need to plan my spacing so that I'm all the way at 1, 2, 3, 4. I think -6 is how far I want to go. All right, let's see how this goes. So now I'm going to put my y-axis a little bit further over here. So again, if you had a printer, you printed it out and you're putting it right on the sheet. If not, again, you're just kind of drawing this here on your paper. Label it, as always. 1, 2. All right. 1/2 x plus 1. There we go. All right, that'll do. There is my original area. And I'm rotating around the line x equals -2. So let me go ahead and do that in a different color. So there's my line of rotation. And then I need to go 1, 2, 3, 4. So 1, 2, 3, 4. And I'll put it in red, I guess. Something like this. All right, I'm going to do my little spinny thing here to show I'm rotating that way. I'm going to put this on calculus in motion. Give me 1 second here. I'm going to pause it. So here's what's going to look like whenever I rotate around x equals -2. Whoa, that looks totally different. Did you catch that? Let me do that again. Watch carefully. It's going to happen fast. Wow. All right, it looks like some kind of bowl with like a triangular opening here. So yeah, let's sweep a disc or a washer here. Wow, this is totally different. Look, your circles are horizontal now. And I definitely have a washer. There is a hollow here. So let me clean this up a little. I want to revolve it and let it stay not as shaded in. Okay, so I'm going to sweep this here. All right, take a look at these circles here. Just look at it for a minute because we're going to do the math in just a second. Try to keep your eye on the inside circle. Do you notice as it goes up, the inside circle gets wider and wider, like the inside circle is getting bigger? Your little radius is getting larger. And my outer circle, if you track your eye on the outer circle here, the outer circle is staying the same. So your big radius should be constant no matter what. And something special is going to be happening here because your cylinder is horizontal. Okay, let's go ahead and try our best to draw this. And okay, here we go. My outer circle, and this is where things can get a little bit crammed on your paper, so just do your best. There's my outer circle. It goes to the outer edges. Now my inner circle is going to hit, and I'm just drawing it here. Whoop. Okay, remember, you draw your radius to the original area, not the reflected area, and you also draw it from the line of rotation. So I'm going to put my pen on the line of rotation, and I'm just going to draw to the right now because your radius is horizontal. This is totally different. So my inner radius is like right here. That's little r. And then big R, again, it's a little crammed on my screen. I'm doing my best here. Little r starts from the line of rotation and goes all the way out to here. There's big R. Okay? So, oh, people, this is totally different. Okay, so I'm chopping horizontally now. Chop, 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 getting washers. But, are you ready for this? In order to get the horizontal, the distance between 2 points, if it's horizontal, I am not subtracting y values like we've been doing this whole time. We are going to subtract x values. So that is why in that video you watched, depending on what period you were, you might have watched it 2 weeks ago, you might have watched it a couple days ago. I need to subtract x values. So I need to find the x value along this function. So that is why in the video, whenever we took our original equation, and our original equation is y equals 1/2 x plus 1. Actually, let me do it up here because that's why the space is there. It says solve for x. In case it's needed, solve for x. If I have y equals 1/2 x plus 1, I'm going to solve for x real quick. So subtract 1 and then multiply by 2. So 2y minus 2 equals x. 2y minus 2. All right, remember that, 2y minus 2. So let's go ahead and do big radius first. That's going to be easier. Big R was constant the whole time. I'm going to take this x value. What x value is this? Like, where is that? Well, that is at 2. It's always at 2. So it's going to be 2 minus, because you do right minus, let me write it out, right minus left in order to have like a positive value. All these things you're going to want to jot down to remind yourself. They're very commonly forgotten. Okay, and the radius goes all the way to here. And what's the x value right here? Well, that's my axis of rotation. That's -2. 2 minus -2 is 4. So your big radius has a length of 4. And that should make sense. You can count it. 1, 2, 3, 4. All right, let's do little r. Little r started here, okay? And that is on the function. So I'm going to take the x value of the function. Well, the x value of the function, what did we just do? We said that x is 2y minus 2. So this x value, which is on the function, is changing 2y minus 2 minus, what's this x value here? -2. 2y minus 2 minus -2 is 2y minus 2 plus 2, which is 2y. All right, this is all very exciting. Totally different. Now, are you ready for this? It's going to get even more different. Okay, so we are not chopping, chop, 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 chop from left to right anymore, right? Our circle, is this thing still going? Ah, yes, our circle is going bottom to top. So we're starting at a y value and going up to a y value. So what y value am I starting at down here? Well, I'm starting at the y value of 0, and I'm going up until what y value? The y value go up until is 2 because these lines intersected at when y is 2. So I'm starting at y equals 0. That says y equals 0 all the way to y equals 2. And I'm still doing pi r squared minus pi r squared. That hasn't changed at least. So pi big R squared minus pi little r squared. That's always going to be the same. Ooh, are you ready for this? Your sentence began with y. Your sentence is about y. So your sentence needs to end in y. Okay, it's in terms of y. Let me go ahead and draw a cylinder again. For this example, our inner circle looked like that. See how like the thickness was like this way? This right here was our height, which we're calling dy. Our height is up and down. Our height is along the y-axis. It's up and down. Whereas here, we had a thickness that went like this way. It was dx. It was along the x-axis. So just remember, if your sentence begins with y's and is about y, then it's going to end in a dy. Okay? I'm going to leave these last two to you to do. Just remember, you're going around an x equals. So your integral should have a y value to a y value. There should be y stuff here, and they're going to be dy for both of them. Okay? dy. And then I'm also going to leave you with this here. Okay, so again, if you have, actually, even if you don't have a printer, this is going to be a PDF posted, so you can just look at the PDF then. The other one, we have y equals x squared. I'm just going to draw the region with you real quick. I'm not doing the problem. I know you know what a parabola looks like. I'm not trying to insult your intelligence. I would just hate for you to somehow accidentally do this whole thing wrong because you drew the area wrong. So I have a region bounded by y equals x squared, y equals 0. Here's y equals 0. And here's x equals 2. Okay, so I need y equals x squared, which looks like that. Okay, so if I know that I'm going to hit up against here at x equals 2, let me go ahead and make this look a little bit better. So x squared has 0, 0. It has 1, 1, 1, 2, 3, 4, and it goes up to here. So here's my parabola. Dang, that looks really bad. Make yours better than mine, okay? X equals 2 and y equals 0. This is the area that you're rotating in various ways. So similar idea to the other one, just a slightly different region. And you might need, spoiler alert, you're going to need, for the last 3, the square root of y. Okay? So that is part of it. Next thing I want to do real quick is just set up some FRQs with you here. And I'm going to give you the copies of these free responses. Okay? Ideally, we would have done this in class, but it is what it is. I'm going to do an FRQ with you here. And I'm going to get my graphing calculator set up. Hold on. All right, here we go. We're going to do our first FRQ here, and this one is from a little bit of a throwback, 2014, but these are some really great visuals. And in class, when I finally see you again, we'll do some newer ones together. One of them will be a quiz, just fair warning, but we'll also obviously just do some practice. Okay. We have a region enclosed by this quartic function, x to the 4th function, the horizontal line y equals 4, as shown in the region. They put r there. Now this can be misleading because big R is what we use for radius, and often they'll put a big R there for like the region of the area. So it is what it is. I want to find the volume of the solid generated when r is rotated along the line, about the line y equals -2. Let's just try to get a picture of this before we go to calculus in motion. I need to extend my y-axis here. Again, you're going to get a printout of this in class. I will give you one to tape. So in your notebook, can you just write down the work? I would label it 2014 so you remember, because you have kind of a lot of video notes going on from the snow days, and the more you label stuff and stay organized, the better. Okay, so make sure you're writing neatly, organizing things. You're not squishing things in a 1 square inch margin of your notebook. You know who I'm talking about right now. Okay, anyway, so y equals -2. Let me draw this dotted line here. So I'm going to rotate this. And if we were in class, I would pause right now and I would have everyone draw the reflected region after going all the way around here. And inevitably, I would end up seeing this people drawing that. Okay. And as I said in the last video, that is a classic mistake that can happen, and we don't want that. I don't know exactly how far apart these are because like there's no scale here. This is calculator active because it's number 2. So I could find out, but we really just want a general visual here. So I'm just going to go ahead and draw my reflected region something like this. Remember, this is question 2. 1 and 2 are calculator active. 3, 4, 5, and 6 are not calculator active. So sketch this with me here. Obviously, don't write the whole question down. I'm giving you that. But draw yourself a little visual here because you're going to be marking it up. So you can't mark it up if you're not drawing it. So at least draw this. And, okay, I'm going to rotate like that. Let's go to calculus in motion and get a sense of like what is happening here. 2014. All right, you ready? Let's make this thing rotate. Woo! All right, all the way down there. And I'm definitely going to have a washer here. And that was pretty cramped, right? So calculus in motion is going to expand this so we can see it a little better, bringing it down all the way around y equals -2. I have a hollow here. So the volume is everything except this inside piece, okay? And, oh, it's not going to spin, or it's not going to sweep one of the pieces here. But I don't want to click volume yet because it's going to give us the answer. Anyway, you can clearly see there is a washer, and oh, actually, I think it was going to do it. Dang it. All right, never mind. It's okay. Let's go ahead and draw it. I saw it too late. Alrighty. So let's go ahead and draw our outside cylinder piece like this, and then our inside one would look something. It would hit both of those function pieces right there. Okay? And this is going to be a dx problem because my width is going this way, like along the x-axis. So there's my dx. Okay, let's go ahead and draw our radius. And this is common error. People want to draw the radius like down here and down here. But the problem is that we always want to go to the original area, which was where our capital R is. So my drawing is not perfect, but we'll do our best here. So we're going to start from the line of rotation, and we're going to go up until we hit our first thing. Whoop, right there. First function, that is little r. Start from the line of rotation until we hit the outer function, and that's big R meaning outer radius. And I kind of want to see something here. Is it going to let us sweep an X? Oh, yeah. All right, there's just a lot going on right here, but I don't even know if you can see that. I was just trying to get you to see that the inside circle was changing, whereas the outside circle was not changing. Okay, anyway, so volume is integral pi big R squared minus pi little r squared dx. Let's personalize it. All right, our cylinders start all the way on the left here. That's where my leftmost cylinder is. And, ooh, actually, what x value is that? I guess I could assume that these intersect at 0, but we should probably make sure. And then my cylinders end right here. Like that's going to be my rightmost cylinder here, but I don't know where these intersect. So that is why we need a graphing calculator. So if you have a graphing calculator, why don't you go ahead and type these functions in. That is my f of x and y equals 4. I'm going to hit graph. And I'm going to find those intersections. I'm going to go down to intersect, enter. Let's find the leftmost one first. Okay, they do intersect at 0. It kind of looked like that, but you should never assume. Always make sure if it's calculator active. You can just find it real quick. Okay, 2.3. So I don't have to worry about storing anything because it's just 2.3. So my circles start whenever x is 0. I'm going to put x here just to emphasize that it's a dx problem. And I need pi big R squared and pi little r squared. Let's write expressions for little r and big R off on the side here. Little r is changing because little r here moves along this curve, this function. So little r could be this, it could be that, it could be that. Like depending on where you draw your cylinder, it could be any of those. So little r is going to be written in terms of a variable here. So, okay, I'm going to subtract y values, a top minus a bottom. So the top y value here is the function itself, and I don't feel like writing this out. So I'm going to call it f of x minus the bottom y value. Well, what's the y value down here? It's negative 2 because that's what I'm rotating around. So I have f of x plus 2. Big R is this y value minus this y value. What's the y value here? The y value here is always 4. Okay, and then I'm going to do minus, what's the y value down here? Negative 2. So what 4 minus negative 2 is 6. Okay, so I have pi big R squared minus pi, watch your parentheses here, little r squared. And that all should be in parentheses with dx. Okay, I'm going to type that in the calculator and then we'll get an answer. All right, typed it in on my calculator here. And this is what I got, 98.867. This is perfect. Let me round it so I don't. 98.868. Okay? 98.868. You could put 867 if you want. Remember, you can truncate. You don't have to round. So we obviously could do part C if we wanted. I guess that wasn't so obvious. Let me just tell you, we could do part C. We're not going to for time's sake. Part B, we don't know how to do cross-sectional volumes yet. You're going to be learning that in a couple days. All right, I have one more I want to do with you. I have two really great ones, but for the sake of time, let's do this one from 2011. I'm a little more partial to this one. This is question 3. So can you use a calculator on this one? Hopefully, in your head, you're thinking, no, because you only use a calculator on numbers 1 and 2. So, okay, here we go. Again, I'm giving you a printout of this as well, but because I want you to mark this up on your notebook, can you label this in your notebook? Can you label this 2011 number 3? And can you just do a quick sketch of this for yourself? Because we want to draw the line of rotation, the reflected region. We always draw little r and big R, even if you don't want to. We always need to. Alrighty, we are rotating. What are we even doing here? We're taking 8x cubed and sine of pi x, the region enclosed by that. Ooh, how do I know which is which? So if you were doing this in class, you'd be doing this in your groups. And the first thing you all would have to do is decide which is which. And hopefully you can see here that the function that's concave up like this, only a cubic would look something like that, okay? And then if you had a sinusoid, specifically a sine function, sine starts concave down at the origin and then switches to concave up. So let me go ahead and label this. So this one is f of x, right? And this one is g of x. Okay, so there's my region. They're calling it capital R here. We know how to find tangent lines. We know how to find area. I really am caring mainly about volume, okay? And we're rotating around y equals 1. Here's going to be my axis of rotation, line of revolution, line of rotation, whatever you want to call it. And College Board was nice. They gave us where they intersected, so we don't have to solve for that. We know exactly where those lines intersect. Let's try and picture this ourselves before we go to calculus in motion and get a visual here. Okay? So I'm going to take this region and I'm rotating it up above. So this is going to be a little rough. It's kind of hard to draw this one perfectly. All right, it's something like that. There's my rotated piece. So let's fire up calculus in motion. And what year was this? 2004? No, we're doing 2011, right? Yeah, 2011. Nope. There it is. Okay, this was number 3. Watch carefully for the volume. Okay, we're going to spread this across just so we can see it easier. Are you ready? Woo! We're rotating that way. And let's go ahead and... Oh, no, I don't want to see that. Shoot. Reset. Okay. So I'm just going to show you one more time. There it is rotating around. And here it is stretched around, and we're rotating up above here. I just want you to look at this volume one more time. Okay, disc or washer. I really wish it would move this washer across. I can't get it to do it here unless I'm totally missing it. No. All right. Oh, whoa. Oh my God. Okay. Yay. Okay. You ready? So I'm starting here and moving to the right. Can you see that circle? I'm hoping you say yes right now. Do you see how the inside circle, which is right here, as I move to the right, that inside circle is getting smaller and smaller until it's getting infinitesimally close to not having a hollow piece at all. And over here, it's almost like there's like no circle. Okay, so but people, look, the inside circle is changing, but isn't the outside circle changing too? This one is special because like a lot of the times, I think the only ones I've done with you, only little r or big R changes. Like they don't both change. In this one, check it out. Little r and big R are both getting smaller. So both of them are going to be written in terms of a variable. Neither of them is constant. Exciting things going on here. So let's go ahead and draw one of our cylinders. I kind of want to do it in blue, just so you can actually see it. All right, so on your paper, draw this with me. Do the best you can, as always. I'm going to go until I hit that outside function. I'm going until I hit that outside function. Mine got a little wobbly there. Here is the width of my cylinder, and here it is going down. Okay, now I need my inside circle, which is right there. From the inside to inside. Okay? You can draw more than one if you want. You definitely don't need to. I'm going to start from the line of rotation. And remember, you draw to the original area. So don't be drawing your radius like this. That is a big no-no. You'll get the opposite sign of what you want. Okay? So I'm going to be drawing to the original area. So let's draw little r first. I start from the inside and then I go down till whoop, I hit something right there. That is where I hit the inside function, that's little radius. And you can see like this looks like the radius of that circle. It should if you drew it remotely close. Then I start from the line of rotation and I go straight down until right there. I hit the outside. Okay, that's big radius. Not to be confused with that R, which they're calling the region. Okay, before I do anything else, let's go ahead and get little r and big R out of the way. So little r starts, okay, I have vertical, right? A vertical line segment. To find the distance between 2 points vertically, I'm subtracting the y values. So the y value here is always the same. It's 1. Minus the y value here is on this curve. And didn't we say this curve was the sine function, which is g of x? So you could do 1 minus g of x or 1 minus sine of pi x. Okay, big R time. For big R, I'm going to be starting here. There's big R. What's that y value? Well, that y value is always 1 minus all the way down here, this y value. This y value changes. It's on a non-horizontal piece. This is my f of x, which was the cubic. So you can definitely call it f of x. College Board called it f of x. You can call it f of x. If it bothers you to have f of x, or if you just like to see the function, you can put 8x cubed. It's not a big deal. So now I'm going to go ahead and write that out. I have volume. I don't want to run out of room. Let me do it down here. Okay, volume equals the integral from something to something of pi big R squared. And you can write it just like this. You will get full credit for that. Pi big R squared minus pi little r squared. And this is a dx problem. All right, where do my cylinders start? Let me just look at this one more time. My cylinders started over here at 0, and my cylinders went to where they intersected. What x value did they intersect at? 1/2. Don't put 1. You want the x, right? You're going from an x to an x. So x equals 0 to x equals 1/2. And I think that's all, isn't it? Yeah, because it says write, but do not evaluate. So that's it. Yay. Okay, cool. So we will finish up with this in class with some more examples. See you later.